Hello, Year 13. So we've got one extra little bit to add to the integration stuff we've done so far, which is finding areas using integration. Now, we already met this idea in Year 12. Integration finds the area underneath a curve. That's what it does. And as a result, we can use integration to solve geometry problems and area problems. The only thing that's new, really, this year is that we have a whole load of new integration techniques that allow us to deal with this with more complicated equations in the areas under more complicated curves. So there's nothing surprising or new here. So we'll do a couple of examples. The first one, example 22, we have a diagram drawn for us. You pretty much always get a diagram drawn for you for these area questions. You might not always, but the vast majority of the time, especially when they're a bit more awkward. So do use the diagram as a kind of helpful cue of what's going on. We've got our function 9 over root 4 plus 3x, and then we're bounded by the curve, which is here, the x-axis at the bottom, and then the lines x is 0 and x equals 4. And what that means is we need to integrate between 0 and 4 the function 9 over root 4 plus 3x. And we can make our life a bit easier because 9 is a constant, so that can pop out. And then we're integrating 4 plus 3x to the negative 1/2. It's a lot easier to deal with it in that format instead of 1 over root, because now we can spot that this is one of these reverse chain rule problems. We've got a linear function inside a standard function, and therefore I can kind of integrate this like normal, but I just have to then multiply it by 1/3. So what I'm going to get is 9 lots of, and then if I was to integrate this 4 plus 3x, I've got to raise the power, so it's a half now, divide by that new power, so that's going to multiply it by 2, and then I have to deal with the fact that I've got 3x in here, so I need 1/3 of this between 0 and 4. 1/3 times by 2 is 2/3. It's another constant, so I can pull that out along with the 9 as well. 9 times 2/3 is 6. So I actually have 6 lots of 4 plus 3x to the half with the limits of 0 and 4. Need to make a little bit more room just to do this quick calculation. So that's 6 lots of, if I substitute 4 in here, 3 times 4 is 12, plus 4 is 16, so that's 16 to the half. And then if I substitute 0 in, that is just 4 to the half. Half is square root, so this is just 4 take away 2. So that's 2, 6 times 2 is 12, and I'm finished. It's worth also pointing out at this stage that your calculator does all this work for you. So if I just hit integrate, and then I want to integrate 9 over the square root of 4 plus 3, and then alpha for x, forwards until I get 0 and 4 for my limits, hit equals, answers 12. So actually this is just a straightforward calculator question. You don't need to do any of the actual on-paper algebra work unless it's a show that question. They might say show that this is 12. In that case, you have to show all the steps. But as a result, this wouldn't be worth as many marks as it used to be, because you should be using your calculator to deal with these, as you can see, way faster than doing it all by hand. But yeah, this is not super hard to do, but your calculator will speed it up. The second type of area question we meet is ones where we've got 2 different curves and we need to find the area in between the curves instead of just underneath them. What you kind of need to remember is, if I separate this up into, here's my function of x, f of x, and the area underneath it, and here's my g of x and the area underneath it. This region R is actually the whole of the area under f, subtract the area under g. This is just something we've met in year 12 already, and actually it's equivalent to those GCSE area problems where you had like squares with circles cut out and you had to find one area and subtract the other. So in order to find this sort of area between two curves, we subtract the functions and integrate, or integrate them separately and subtract the two answers. Those two things are equivalent. And therefore we can tackle problems like example 23. So I've got f of x here, which is just sine 2x, and g of x, the red curve, which is sine x cos squared x. And I want to find the region. So I need to integrate between 0 and pi over 2 f of x minus g of x. So sine 2x minus sine x cos squared x dx. And that's equivalent to integrating sine 2x and then integrating sine x cos squared x and then subtracting. You can manage it and organize your working out in either of the two ways. I'm not going to go through in detail where these come from, but suffice to say, sine 2x is a function of a linear function, like we saw a minute ago. So we integrate the sine function and then we divide it by 2 at the end. So what we end up with is negative a half of cos 2x. And then our second one, this is a reverse chain rule function. It's a function and its derivative. If you want a bit more detail, there is a very similar question to this in example 9 earlier in the chapter, just to show you what's going on. But suffice to say, that one is 1/3 of cos cubed x. And I want to do this between 0 and pi over 2. However, just like with example 22, all of this algebra work and getting from here to the, from the integral to here is all completely pointless if all they ask you to do is find the area, because we can just use our calculator to do this. I just want to integrate, and then I can just type in sine 2x. You must remember to close your brackets after the trig functions, otherwise it will mess everything up. But there we go. Subtract sine of x, close that bracket, cos of x squared. So sine x cos x squared. Remember, on the calculator we write cos x and then the squared, unlike by hand where we write cos squared of x. It's just because they mean the same thing. It's just notation. And then I need my limits between 0 and pi over 2. Remembering, of course, that because we've got a pi here, we need to be in radians, which my calculator is. And then I just hit equals, and oh look, the answer is 2/3. Again, the calculator does all the hard work for you, unless it's a show that question, in which case you have to do that digging through and showing what all the integration steps are. But don't forget, your calculator does a great deal of the legwork for you, and all we're really doing is applying all of our new integration techniques to tackling slightly more awkward problems.